All right, good morning. Today we're going to talk about chapter 3 of our Top Hat, which is about the different various states of matter that things can go into. So we're going to be talking about matter instead of energy, and basically that can be in one of three common states, either a gas, a solid, or a liquid. And we're going to talk about that today. So as I said, there's three different states of matter: the solid state, the liquid state, or the gaseous state. And those are states of matter that any type of matter can be in. So what those three states of matters have is they have some rather distinct properties about them, which allows them to have certain behaviors that you associate with each type of state. So for instance, when you think of a solid, you kind of think of a certain kind of rigid thing, maybe a little bit denser type of material, but very, very fixed shape, very set properties, not very compressible. And those states are very different than the states you might think of for a liquid, which is very fluid, very motionable, very different, or a gas, which is very different than both of those. And each state has very distinct properties. They have distinct properties of density, distinct properties of a shape, how fixed that shape is, whether it's flexible or not, how compressible those states are, and then also expansion, how much they contract or shrink when they heat up or cool down. And you can see from this image right here, just three examples of either a solid, a liquid, or a gas. And you can see that the different types of molecules are in different orientations in those distinct states. So in the solid, everything's very close together. The molecules are physically in contact and they're holding on to each other and they retain a shape. Liquid molecules are still in contact, but they're able to roll around each other. And the gas state, there's no contact between the molecules, which allows them to expand to fill up the container that they're in. So the first thing we're going to talk about is density. Density is the mass per volume of an object, and it's something we've talked about before. Again, density is just the mass of something, m, divided by its volume. And when you look at the density of an object, that's going to be a pretty distinct property for every object. Every object has a density that you can calculate. You can calculate how large it is. You can calculate its volume, its area, its width, its height. You can put it on a scale. You can measure its mass. And then you can figure out the density. And usually matter that's solid has the highest density than any other state. So solid densities have very, very high densities. Liquids also are pretty dense. And then the gases usually have the lowest state. So the gases usually have the lowest state of matter densities. And that's because gases can expand. They'll take up the entire container. Solids have very rich, rigid location, very rigid structure, and they're usually, all those molecules are confined to be touching each other. But then when you look at the gas molecules, those gas molecules are very far away and they're not touching each other. And that generally makes the volume of the gas very large for the same amount of mass, and then a very, very low density because you're dividing a number by a very large number down here, a very large volume, and that makes your gas very, very low density because you're dividing by such a large number. So that was one of the properties that the molecules have. Another property that molecules have is their shape. Shapes are fixed for a solid versus a liquid. So if you think about something in the solid state, right, a very fixed shape, look at your computer in front of you, your phone in front of you, any of the chairs you might be sitting on or the floor you're standing on, right? Those are very solid objects, very fixed shape. They don't move when you step on them. They don't move when you touch them or hold them. Versus something like a liquid, the shape will change and it'll adjust to the shape of the container. So if you look at something like this bottle right here, the liquid in this bottle is shaped a certain way, and it's bottle shaped. If you were to pour the liquid from the bottle into the spoon, it would go from being a bottle shaped liquid to a spoon shaped liquid. As the liquid moves from one container to the other, the shape changes of the liquid. Liquids will always take the shape of their container, but liquids have a fixed volume. So you can see here again, the liquid line right here, the liquid doesn't expand anymore. It can't take up the entire bottle because the liquid doesn't have enough volume to fill the whole container. Gases will. Gases are interesting. They'll take the same shape as their container like a liquid would, but they'll also expand up and fill the entire container. So gases have very flexible volume. They could be either very dense gas like the one up here, or they could be a looser density gas that's taking up the whole container. Another example here, you can see that initially the gas is all in one container with this stopper kind of blocking it, so the gas molecules are able to move around but not leave. As soon as we open up that stopper, the gases leave from one container to the other. They fill that container and they take up both volumes. So the gas's density has gone down as it takes up a second location and fills up a larger container. And as that expands, the gas expands to take up both containers. Gases will always expand to completely fill their container. And you might notice that even with bottles of perfume or bottles of scents, right? You open up that lid, you take off that lid, within a few minutes, you'll smell that gas as that gas goes from filling up the bottle right here to filling up the entire room as they expand to fill the new container, which is the room. So we've talked about shape, densities of gas, we've talked about the shapes of the gases. You know, if you think about why can molecules change shape, why can solids not change shape, why can gases change shape, that all has to do with the forces that are holding those molecules together. Those molecules are held together by forces that hold the molecules, not the atoms within the molecules, not the carbon connected to the hydrogen, but that molecule together is going to be interacting with other molecules. And solids have really, really strong forces between those molecules holding them together. Solids are held together very strongly. And that results in solids having a very fixed shape. Those molecules don't want to move. Those molecules don't move to other places in the lattice. They stay together. Those molecules hang on to each other very tightly. They don't move around. So those molecules are in a fixed position. That means that solids have a very, very fixed shape. Liquids still have pretty strong forces between the molecules. They're still hanging on to each other, they're still touching, but the molecules can kind of roll around each other. So it's like if you had a bunch of tennis balls in a bag, and think of that as a liquid, right? The tennis balls are still touching each other. If you lift the bag up, the tennis balls all go together, but then if you put it down on the floor, the tennis balls can kind of spread out and still touch each other, and that's like a liquid in a container. They can move around, they can roll around, and they're still touching each other, but they're not taking on any fixed shape. They take on whatever shape the container gives them. So that's an example of how liquids can change their shape, but they still have a fixed volume, because no matter what you do, you can't have more tennis balls. You're not going to have more tennis balls or less tennis balls in that container. So the liquid's always going to have the same amount of tennis balls. So the shape, even though the shape changes, the volume stays the same. But gases don't have to worry about changing, have fixed volumes, and gases don't have to worry about fixed shape, because in the gas, all those molecules are very separate. So rather than having a bunch of molecules that are kind of close together like this, gases, they're all very far apart, and they're actually not touching each other. So in a gas state, like here, all the molecules are very far apart from each other. All the molecules don't touch each other. And because of that, the molecules are very far apart, no cohesive forces at all between the molecules, and they're free to move around every which way. And every single molecule is free to move in a different direction, which means that the gas molecules are really far apart from each other, they don't really touch each other, and they don't really touch any of the containers that they're in. So they're able to kind of move around until they hit the wall. So they move around, this molecule is going to go here, it hits the wall, goes somewhere else. This molecule goes all the way down here, hits the wall, goes up here, hits the wall again, goes somewhere else. Those molecules are always moving around, and they're kind of expanding, moving around. That means the gas takes up all that space. The gas has all this area to take up. So the gas takes up a very large volume right here. You can see gas taking up a really big volume, versus the solid or the liquid, the volume is confined kind of to the area that the molecules are touching each other. So you get a really different kind of shape. You get gas behavior where gases can expand, take up a whole container. Gases have a very low density, again, because of this low force between the molecules. Gases don't have a fixed shape because of this molecule. So these are all different properties of gases, all because these molecules are far apart and not contacting each other, no cohesive forces between each other. And that ability for the molecules to touch each other, that cohesive force between the molecules, also means that solids and liquids and gases have a certain degree of how compressible they are. So if you think about a solid or a liquid where all the molecules are pretty much touching each other, there's not much space between the molecules because they're already touching for you to put another molecule. Versus if you look at a gas with lots of space, we have all this other available location to put new gas molecules. So gases have a lot of space between the molecules, and we could keep putting more and more gas molecules between them until we got down even to a solid, liquid or solid state. But there's lots of space between the gas molecules, which means there's lots of space to put more and more gas molecules in. And that's why if you look at how compressible or how much you can push on an object, gases have a very high compressibility, significantly higher than the rest of than either the liquids or the solids. And again, that's due to the fact that gases have such a low density. Their container has a lot of gas molecules there, but there's lots of space between those gas molecules, and there's a lot of empty space that a new gas molecule could be pushed into, or an existing molecule could be pressed down and put into. So if you think about a balloon, and you try to hold the balloon or you try to squeeze a balloon, right? What happens? You squeeze a balloon, the balloon kind of moves around a little bit. The gas can get compressed a little bit. Or even just filling a balloon. When you inflate a balloon, you're taking air from your lungs, you're pushing it into the balloon, and you're putting a lot more air into the balloon than would normally be in that space. And if you want to prove to yourself that you have a lot more air in that space than you would normally have, well, fill up a balloon and then let go. Because all that extra air is then going to leave the balloon and the balloon will fly away from you. Because you put more air than was normally in that amount of space, you've compressed that air into a smaller space, and you've gone from a state more like the green to a state like the green and the blue. The green is the air that was normally there, the blue is all that extra air that you pushed into that balloon. And that puts a lot of gas molecules in a small amount of space. You've compressed that gas. Same thing happens if you have your gas grills at home, or if you go to a barbecue. Gas grill like that, propane tank like that, what they do is they take a gas and they put lots and lots and lots of gas molecules all into a container like this. And that's a gas under a lot of pressure. And there's a lot of pressure in that gas to hold all those gas molecules in a very small space. You can't really do that, on the other hand, with a liquid or a solid. So solids and liquids have a very low compressibility, not very compressible molecules right there. And that's because the liquids and the solids don't have much space between them. They're already pretty tightly packed, right? If you try to put another molecule between these molecules that are already touching each other, there's no space for another molecule. There's not space to really put another solid molecule right here or here, because we've already got the molecules as close as we can get together. And because of that, you can't really push any more liquids into the same space. So if you tried to push more liquid into this bottle, it's just going to come back out because the bottle's already full. Or if you try to put more rocks into this bottle here, they're not going to hold any more because this bottle's already pretty full. You can't put more rocks into this bottle. Solids don't compress the same way that gases do. And that's why molecules in the liquid and solid state, because they're so close together already, you can't really put them any closer together. They have a very low compressibility, but gas molecules have lots and lots of space between them to allow those molecules to kind of compress together even closer together and still remain a gas for a good amount of time. You have to compress lots and lots and lots of molecules together to go from a gas back to a liquid. So even if you compress a gas a couple hundred times stronger, than it normally would be, you're still going to remain in the gas state. You're just going to be a little denser gas than you normally would be. And then the last property of gases or liquids is how much these things can expand or contract if you change the temperature. And temperature does change with volume. So volume changes with temperature. So if you take a liquid at hot temperature or a liquid at low temperature, the volume does change a little bit. And if you want to try this at home over the next few days, you need to get a really accurate measurement, like an really accurate measuring cup or things like that, or a volume flask. And if you take one of those and you put liquid that's really, really cold, so not ice, but fairly cold liquid, freezer temperature almost, and then you heat it up, and you heat it up in your very slowly over time, and you have a very fixed volume to begin with. If you heat it up to almost boiling temperatures, you'll note that the temperature, the liquid volume will be a tiny bit higher than it was before. And that's because liquids in the warm temperature, high temperature state do take up a slightly larger volume than liquids in the low temperature state. So if you had a bottle full of water at a certain temperature that was really cool, and then you heated it up, you would watch that volume go very slightly high, but it's not very significant. Solids do expand, liquids do expand, but nowhere near as well as gases do. Gases really expand a lot. So if you take a balloon at room temperature right here, and you cool it down in something like liquid nitrogen, it's going to get really, really tiny. It's going to really contract. Gases really are sensitive to temperature changes. Gases get smaller and closer together and lower density as they cool down, and as they heat up, they expand. And you can check this with your air tires in your car. So it's a relatively cool bit warmer day today. If you were to check the air pressure in your tires, you'd get a certain number. And if you were going on a colder day, you'd get a colder, lower number. So on my car, when it was cold last week, it was about 20, 30 degrees out. And the pressure in my tires was reading about 32 PSI. And then when it was warmer again, when it got up to almost 70 degrees, so we have our temperature over here. And then when we went out to the car that day, the pressure in the tires read 38. So you can see that the pressure, which is due to the volume of the gas, went up. So the volume of the gas at higher temperature took up more space, it expanded, and that resulted in a slightly higher pressure. My tires became slightly more inflated. So gases are very, very sensitive to thermal expansion, and it's something you have to keep an eye on with your car. But this does happen with solids and liquids, so it's something you have to keep an eye on for your car with your tires. But if you notice also in this picture right here, there's also another thing in this picture, and that's this bar down here along the ground. And this is for expansion as well. So solids do expand when they heat up, but they expand over a very small amount. But what this bar is on a bridge, and bridges are very long. So this bridge is a couple miles long, and you can see these little holes right here. And these holes in the bridge are called expansion joists or expansion grates. And that's because on a cool day, this bridge is going to shrink a little bit. And if a bridge were to shrink and it was all one piece of concrete, it would crack, and that's not very good. So instead, they put these special bars in the bridge that the bridge is held together, but the bridge can shrink, and these little gaps, these little holes, will get bigger as the bridge shrinks when it gets cool. But then when it's summertime and the sun starts shining on the bridge, there's some holes here that the bridge can expand to. So you can see how these kind of lock together. So this bar here, and then this bar here. Each one of them's not touching, but there's that gap in between them. So as the bridge heats up at a warmer day, the bridge will start to expand to fill in those holes. The bridge gets larger, and then if it cools down at night, the bridge will contract again. And this is so that the bridge can get bigger without buckling or cooler without cracking, because solids do expand as well. Solids expand with temperature just like liquids and gases do, except solids, the really only way to notice this would be on something really, really large like a bridge. To be very noticeable. But your gases are going to expand the most, but solids and liquids are going to do this as well. So we can kind of think about solids and liquids and gases with a couple different properties, right? We talked about that they have a fixed shape, they have a compressibility, they have different properties. They have properties of density, they have properties of compressibility, properties of thermal expansion, properties of shape, volume, fixable or not. But then we could kind of think about, like, when you think about a state of matter, which of the kind of descriptions best describe it? Solids have a certain set of properties. Liquids have a certain set of properties. Gases have a certain set of properties. And if you were to look at these four descriptions here, you might notice that one of them describes a liquid a bit better, one describes solid a little bit better, one describes a little bit gas a little bit better. So, right, so we know that we're talking about solid here, and solids do have fixed shapes. Solids don't go changing their shape. So we can rule out these other two right away. We know it's not this one because solids are not flexible. We know that solids aren't flexible, so we're ignoring both of those. But we do know solids have a fixed shape. And in terms of how compressible things are, solids aren't very compressible because solids have all that space between the molecule, don't have very much space between the molecules. If there's not much space between a molecule, solids can't compress. So in our case here, our solid is a liquid, or a solid is a low compressible, fixed shape material. and it doesn't change too much in that regard. And then same thing, we could look at a gas. How is a gas different? So this is our final answer right here, is this one right here. So we've got fixed shape material with low compressibility. And if we were to compare that to the state that a liquid is in, or a gas is in here, we know that gases aren't fixed shape. Gases can expand to fit their container. Gases will take up the entire container. They won't take much room. They'll take up the entire container. They'll be very flexible. They can, if it's a small container, they'll fit it. If it's a large container, they'll fit it. If it's a round container, they'll fit it. So gases are very, very flexible materials. So they're not in that fixed shape category. They're more in this flexible category right here. So we can rule out those first two answers completely. But now we have to look at, is it compressible or not? And gases, again, have lots and lots of space between their molecules. So gases are highly compressible, which means that our gas is a flexible shape with a high compressibility versus our solid is a fixed shape with a low compressibility. So we've got two different kind of statements. One describes a gas, one describes a solid. And if we go to our pictures here, you can see, right, solid, all the molecules very close together, in contact with each other. Those solid molecules are not taking up any more space than they need to be to touch each other. They're very fixed because they're hanging onto each other very well. And you can see that the solid is keeping its own shape, this square type shape, even though the container has a very different shape. So this container is a triangle shape, but the solid is a square because solids maintain their own shape. It's a fixed shape, and you can't really push any more on these molecules to push them closer together because they're the closest they can already be. You compare that to the gas down here, though, very different story, right? The gas has become flexible and it's taken up the entire shape of the container. And if I were to make this container even bigger and make it a shape like this, then you would see this molecule move over here, this molecule move here, this molecule would move here. These molecules would move around, and your gas would now have a different shape. Gas would be even more different shape again, because gases are flexible in their shape. They can take on whatever shape their container has. So gases have a change in shape. And then the option of how compressible it is. Compressible, there's a lot of space between these molecules, lots of room to put more gas molecules or to push the gas molecules into a very tight container. So this is a very flexible material, but it's also a very highly compressible material as well. So those are just some properties of matter in terms of compressibility, shape, volume, density, thermal expansion. And you'll see that different states, the gas, the solid, the liquid, they'll all describe differently in terms of that. And that leads to our new, what we'll talk about next, is we're going to talk just about gases. So we're going to focus on gases for a while because gases have some properties that are pretty neat, right? The gases will expand, they'll fill their container. They have a relatively low density because of that. Again, look at all this volume right here. Very large volume over an area. So very large volume, very low mass. Here, so the mass of the molecules right here is pretty low, volume's pretty large. Because you have a low mass over a very large volume, then that means that you have a very low density, because density is just mass over volume. Here, that's because gases expand to take up their whole container. Gases are also very, very compressible because there is all this space that the gases take up that you could put either more molecules into, or you could push these molecules all down into a much smaller area and still have a gas state. So you could make this very, very compressed and still have a solid gas, more expansibility. And it turns out there's a bunch of mathematical equations that can be used to predict and model this behavior. So we can do that for these different states of matter, and we can do that especially for the gases. And there's a series of equations that can be used to predict the behavior of the different gases. So the first equation that we can use is this law called Boyle's law, which is a gas law or a chemical equation, mathematical equation, that can predict how does the pressure of a gas compare to the volume of a gas. So we've got pressure, and pressure we're going to just be using the symbol P, and then the volume of a gas is the V volume, and that'll be V. And what Boyle found when he looked at these molecules and when he looked at gases and how they behaved, what he saw is that the gases kind of had a constant pressure volume effect. So don't change the temperature of a gas, leave the temperature the same. So we're not going to change temperature, we're just going to leave temperature alone. So if we're in a room right now, we're leaving the temperature alone. If we're somewhere else, we're leaving the temperature alone. We're not changing the temperature. But what he's found is that if you left the temperature the same, the pressure and the volume were kind of related to each other. So the pressure and the volume of a gas at one condition, so with one pressure and one volume, if you compared that to the pressure and volume at a different set of conditions, so condition 1 versus condition 2, there was a relationship there. And that comes up like if you think about two different size containers of gas. So you have a gas container here, and originally the volume was at a 10-liter number. So the original volume, 10 liters here. The original pressure, 1 atmosphere here. So original pressure, 1 atmosphere, 10 liters. But if we were to change the volume of this container, so maybe this is a cylinder that we can push on and change the shape of, or something we can somehow change the shape of it. If we were to change the volume of this container and make it smaller, but leave all the gas inside, the gas isn't allowed to leave the container, but the container were to shrink. So our new volume is only 7 liters. So we've gone from a volume of 10 liters to a volume of 7 liters here. What would happen is we would see the pressure inside the container would increase because the same amount of gas is now in a smaller container. And because the same amount of gas is in a smaller container, the pressure that that gas exerts, or in a container here, how often a gas hits the wall. So if you have a gas, pressure is just a measure of how frequently the gas molecules are colliding with the walls of the container. And if you have the same amount of gas molecules in a smaller container, they're going to hit the sides of the container more often, and that means that the pressure of that gas is going to increase. Or if you were to do the opposite case, and you were to make an even larger container, now the gas molecules don't hit as often because the volume's larger for the same amount of gas, and the pressure decreases. So the pressure and the volume of a gas are linked to each other, and if you increase the pressure of a gas, you decrease the container. If you decrease the container, you increase the gas pressure. If you decrease the pressure, increase the size of the container, you decrease the pressure. And then if you decrease the pressure, the container also becomes larger. So you can check that by looking at the pressure times the volume of one state of gas compared to the pressure times the volume of the second state of gas. And you can see we did that here with this calculation right here. We just took the initial pressure, the initial 1 atmosphere, and the initial volume, the initial 10. Those are those. And then we were solving it for the final condition down here. So we have that one set here, we have the other set here, and it turns out that 1 atmosphere times 10 liters is the same as 1.4 atmospheres times 7 liters. So pressure volume at this condition and pressure volume at this condition are the same for that. And that's the same for any gas at the same temperature. As you change the pressure and the volume, they'll adjust. And this is an example of a calculation here. You can see in this particular example, we're looking at 2 different pressures and at 2 different volumes. So to start this one off, we would look and see, well, which conditions go with which set. So we have 2 different conditions here. We say that the volume here was decreased from the initial volume. So this is our initial volume of 100. The original volume also, if we continue on to read, the original volume or the original pressure was 1 atmosphere. So those are connected. 100 liters of volume and 1 atmosphere of pressure is one set of conditions. And then the second set of conditions is the 75 liters, and we're figuring out what the new pressure is. So we've got new pressure, a new volume, 75, and we're going to solve for that pressure. So we go to our original equation right here. We can see our 2 conditions, our original and our new. And then we just plug things in. So we know that 100 liters goes with the 1 atmosphere. So we put those on this side right here, 100 liters in 1 atmosphere. And then we also know our new condition of 75 liters and some pressure that we're going to have to solve for. So if we do that, we have our set of conditions here. 1 atmosphere times 100 liters is going to be equal to whatever the final pressure is in atmospheres times 75 liters. And to solve for this missing pressure right here, all we have to do is multiply by 1 times 100 and then divide by the 75 liters. Our liter here would cancel with the liters here, and we would be left with a pressure in atmospheres. And then you can see here we do that. So 1 atmosphere times 100 liters is equal to 1.33 atmospheres times 75 liters. And that's the final answer for this question here, looking at how pressure changes. So we can see as the pressure decreases, it goes from 100 to 75, pressure goes down. And as pressure goes down, the volume, as the volume goes down, the pressure increases. So you can see here pressure goes from 1 to 1.33, volume goes from 1 to 75. Volume goes down, pressure goes up. And that's how Boyle's law works. And this is just another example here showing the same thing, and this is actually how we breathe. So when we breathe, our lungs inflate. So when you take a deep breath, your lungs get larger and they have a lower pressure inside it. And when your lungs have lower pressure inside them, the pressure goes down. That means that air from the outside of your lungs can go into your lung. And then when you breathe out, then you decrease the size of your lungs get smaller, and that causes the pressure to go up inside your lungs, and that pushes air out. So you can see that drawn here on these pictures, but we can also do this calculation. Your lungs have a volume that fluctuates between about 4.5 liters and 5 liters, depending on if you're breathing in or out. And what they're looking at here is they're looking at some conditions of pressure in a lung. So we're going to use that same condition, the initial pressure, the initial volume, and that's going to be equal to the final pressure times the final volume. And we can rearrange this equation, right? We're going to be calculating, this is asking us what is the pressure in a lung. So we can rearrange this equation so that pressure is on its own. So pressure is over here, that means we just divide by volume over here, divide by volume. So we move that volume down here. So pressure is equal to the pressure and volume of one condition divided by the volume in the new condition. So what we can see is here at 4.5 liters, we have a volume of 1.02. So we have a pressure of 4.5 liters and we have a volume of 1.02. We can put those two values together, and then the other volume that we don't have a pressure for is the 5.0. So we'll put that one down here. So we'll have 4.5 times 1.02 divided by 5.0, and that'll give us a pressure in the lung. So if we put those in here, 1.02 atmospheres times 4.5 liters divided by 5.0 liters, again, liter here cancels with liter down here. The only unit that's left is atmospheres, and atmospheres are a unit of pressure, so that makes sense. And if we do that calculation, we can see that the fully inflated lung, the lung that's inflated, got a lot of space taking up, that's got a lung volume of 5 liters, and it only has a pressure of 0.92 atmospheres. Since the air around you is about 1.0 atmospheres, that means that the air pressure gets pushed into your lung when you inflate your lung, and that allows you to inflate your lungs with air and oxygen. And then when you decrease the pressure of your lung, or decrease the volume of your lung, you increase the pressure over here. You go to 1.02 atmospheres. And again, since the outside pressure is only 1.0, that means that air gets pushed out of your lungs and back out into the air, into the atmosphere around you. And that lets you breathe out all the carbon dioxide that's inside your lungs. So you're able to breathe in new oxygen by making your lungs larger, making the pressure go down. And then you're breathing out by making your lungs smaller and pushing air out of them. So that's Boyle's law, looking at how pressure and volume are connected. And we use that for breathing is one of the really key examples of how that works. So for the next gas law, one of the important things to remember is that we do have to use Kelvin instead of Celsius. So Fahrenheit is 1 unit of temperature that is used. Celsius is the one used in a lot of the metric and SI units around the world, but Celsius isn't going to work for these gas laws that we're going to be looking at now. So even though we often use Celsius in chem class, we're actually going to be using this Kelvin scale here when we're working with gases. So it's really important that we use the Kelvin scale because otherwise we'll get the wrong answers when we do our calculations. And converting to Celsius and Kelvin is actually pretty easy. So as long as you're in Celsius, if you want to go to Kelvin, all you have to do is add 273 to it. So if you had a temperature of 0 degrees Celsius, like over here, that's the same as 273 degrees Kelvin. Or if you had the temperature of 12 degrees Celsius, then you could add 273 of it and be at 285 Kelvin. So just whatever your Celsius temperature is, add 273 and you have Kelvin. So it's a relatively easy conversion to make. If you want to go the other way, go from Kelvin back to Celsius, just subtract 273. So if we got 373 degrees Kelvin, that's the same 373 minus 273, that's the same as 100 degrees Celsius. So converting between Kelvin and Celsius is really important, especially when we're working with gases, because gases need to be done in this Kelvin scale. Otherwise, you'll get the wrong answer on your calculation. So this next gas law is Charles' law, and this is a law that describes how does the volume and the temperature of a gas look combined together. How do those interact? So for these cases here, the pressure is being kept constant. We're not changing pressure. We're only looking at volume. We're only looking at temperature. So the volume may change, the temperature may change, but it's the same gas. It's the same container. We're not changing the pressure in the container. The pressure in the container is just changing size based on the temperature. And you can see that. It's just basically saying that the volume and the temperature are related to each other by division. So the volume and temperature of one condition here, and the volume and temperature of a different condition here. So volume divided by temperature 1 is equal to volume 2 divided by temperature 2. And you can see that with these balloons here, right? We got this balloon here, it's got a certain volume at a certain temperature, and when we change the temperature, make the temperature go down, the volume also goes down. So temperature goes down as volume goes down, and temperature goes up as volume goes up. So if T goes up, V goes up. So if temperature goes up, the volume will as well. And the same thing for going down. Volume will go down as temperature goes down. And you can see a calculation of that here, right? So we got half a liter container at about 300 K. That's our temperature, round room temperature. And then as we cool these balloons down a lot, we go from 300 K to 250 K. This is our final condition over here. Then we go from a volume of half a liter at 300 K to a volume of 0.42 liters at 250 K. So if temperature goes down, volume goes down as well. And the same thing if we were to heat these balloons up, then they would go from a small volume at a low temperature to a larger volume at a high temperature. So they go both ways, with the volume increasing or decreasing with the temperature. As temperature goes up, volume goes up. And that's one of the units. And then what also though, right, what if we want to use pressure, volume, and temperature all at the same time? We can do that too. So if you take the Boyle's law is this one here, P times V is equal to P times V. Or if you take Charles's law, and that's the one with the temperatures, V over T is equal to V over T, put those together. we already have a V, right? So we're going to put the P with the V like we did here. And then we're going to put the V over the T like we did here. And then you get what's called the combined gas law. It's got that PV. It's also got that T element. And you could look at it for one set of gas at two different conditions. So initial condition, initial pressure, initial volume, and initial temperature. And then the new pressure, the new volume, and the new temperature. So this is a nice little set of equations that we can use to look at all three of those. It looks at pressure, it looks at volume, it looks at temperature, and it looks at those three under two different conditions. The other nice thing about this particular equation is that as long as you have this equation, you don't need the other two. You don't need Boyle's law, you don't need Charles's law, you can just use the combined law. Because if the temperature doesn't change, you can ignore it like we're ignoring here, right? And if we ignore temperature, then we get P times V is equal to P times V. We get the same law. We don't need temperature. And the same thing for pressure. If the pressure doesn't change, we can ignore it and we can get rid of it. And if we do that, again, we get V over T and V over T. We get Charles's law. So we can ignore the one if something doesn't change. So you only need really this equation, but you can use the other two as well. But this one does both those equations at the same time, and you can do any kind of calculation you need. So that's this combined gas law. The only thing, again, to remember, though, is that the temperature units are really important. So temperature units are important. Make sure that if you are using your temperature units, then you want to do this calculation. Make sure that you use Celsius units, not Kelvin units, not Celsius units. So don't use Celsius. Make sure if you see a Celsius unit, convert to K, because if you use Celsius, you're going to get the wrong answer. And just to show that example here, right? If we do this calculation, we're looking at a gas tank. We're looking at a gas cylinder. So it was a 3-liter gas cylinder at 1 atmosphere at 25 degrees C. So that's our initial set of conditions. And then we're going to calculate what's the final set of conditions. Final conditions, we're figuring out the new pressure in a 4-degree room, and the cylinder stays the same. So we're going to keep that the same. So this is our final conditions here. Got our final conditions, 3 liters, 4 degrees, and whatever the pressure is. And now you can't just go and put the numbers in Celsius. So we do that. Try to do that, right? 3 liters, 1 atmosphere, 25. Put all those numbers over here. And then we put all the other numbers, the 4, the 3.0 liters again, and the new pressure that we're figuring out over here. It looks like it all works, right? If you look at numbers, things work out, right? Liter, atmosphere, C, right? We just got to rearrange. So we're going to move the 4 up here. We're going to move the 3 down here. And then if we do that, right, liters cancel with liters, degrees C cancel with degrees C, and we're left with atmospheres. And that number works, right? The units make sense, but we didn't convert to Kelvin. And if we did this calculation, it would look like our pressure went all the way from a room temperature, basically the room you're in right now, and just put it in the refrigerator. The pressure goes from 1 atmosphere down to 0.16 atmospheres. That's really, really low pressure. And as you know, so if you took your bottle of milk, a gallon of milk, and you put that in the fridge from room temperature to refrigerator temperature, according to the calculation we just did, the pressure in your milk container went down by about a factor of 9. So it went down by 90%. And that would mean that your milk container would just kind of collapse down to about the size of a soda can. And we know that doesn't happen, right? So you can go check this out and try it. It doesn't happen. And you know that doesn't happen, but the calculations say it would. But that's because these calculations are wrong. We use Celsius instead of Kelvin. So if we use the right equation, the one we're supposed to use, using Celsius and Kelvin instead of Celsius, converting, then we can see again what happens. And now we're going to use the right conditions. So we take our 273 degrees Celsius, 273, and then we add it to 25, and that gives us the initial temperature of 298 Kelvin. So that's our 298 Kelvin, that's our temperature there. And then same thing for the other temperature, the 4 degrees. 4 degrees plus 273 is 277. So we have our new temperature and our old temperature. And now we're not using 25, we're using 298. We're not using 4, we're using 277. And if we do that, we're going to begin solving for this pressure here. So to solve for this pressure here, we're going to divide by 3. So divide this side by 3, divide this side by 3, multiply this side by 277, multiply this by 277. We're left with only the thing we're trying to solve for there. So 1 atmosphere times 3 liters times 277 Kelvin divided by 298 Kelvin divided by 3 liters. That gives us a pressure of 0.93 atmospheres. So now we only have a very small change in pressure when we go from room temperature to refrigerator temperature. And that makes much more sense in terms of things we've observed and actual calculations. And that's because we use the proper units now, proper units Kelvin. It's really important that when you do this, you use Kelvin, not Celsius, for gas unit calculations. So that's an example of using these, and it is really important that we use the right units. So this is one more example. So this is a little example from about this time last year. So this is Sam the dog. Sam the dog was sent into space by some students in the UK, and it was part of a science project. So they took a big balloon, you can see the balloon back here, and they have a little rope right here connecting to him. So he's got a rope, he's connected to this balloon, there's a little camera, and then they basically took this dog and they let him go up. And he went up to an altitude of 15 or 25 kilometers, or about 15 miles above sea level before he came back. So he had a GPS tracker in him, and they tried to catch him down, and they actually were able to put out this kind of nationwide search to find him, and they found him when it landed. So this was a dog that was sent into space as a toy. But you can kind of see how the pressure in the balloon changes as the balloon gets higher and higher. So what we're going to do is we're going to look at what pressures this thing experienced and what volume changes happened as this dog went higher and higher and higher into space. So we take the balloon that we're looking at here, and we've got a few different conditions. So we've got our initial equation here, P1, V1, and T1, and then P2, V2, and T2, or PF, VF, TF, the final conditions. And then we're looking at where everything goes to. So first we got to convert to Celsius or Kelvin. So we do that first. We make sure our temperature, right, because we have 22 degrees Celsius here. We got to convert that to Kelvin, otherwise we're going to get the wrong answer. So let's do that right away. We know that to convert Celsius to Kelvin, you add 273 to the temperature. So 22 degrees Celsius, that's the same as 295 degrees Kelvin. So we have our sea level conditions, our 1 atmosphere, 6-liter balloon, and 295 degrees Kelvin. So that's one set of conditions over here. Our second set of conditions that we want to look at is the final conditions, right? Final condition at this height, the pressure is 0.45 atmospheres. So we got a pressure. The temperature is 21 C. So we get temperature. So we're going to solve for volume of the balloon. But first, we have to convert volume into, we got to convert temperature into Kelvin. So let's do that. 21 degrees Kelvin, that's the same as 273 plus negative 21 degrees Kelvin. That means our new temperature is 252 kelvins. So we've got a pressure, we've got a temperature, we're solving for a volume and everything else we have. So we just plug those in. 1 atmosphere over here. We've got 6 liter volume balloon, and we're at a temperature of 22 degrees, which is the same as 295 kelvins. So we get that set of conditions. Other side, when we get up into space, pressure goes down quite a bit to 0.45 atmospheres. Temperature goes down a little bit too, goes down to 252 Kelvin. And we don't know what the volume is, that's what we're solving for. So we're going to multiply by 252, put that up here, divide by 45, put that down there. And when you do that, you just plug in everything. 1 atmosphere times 6 liters times 252, divided by 295, divided by 0.45 atmospheres. And if you do that, right, atmospheres cancel, kelvins cancel. The only thing we're left with is liters. And since volume is measured in liters, that's a good sign that we set everything up right. So as this balloon went higher and higher into space, the balloon went from a volume of 6 liters to a volume of 11.4 liters. So the volume almost doubles in size as the balloon goes higher and higher and higher into space. Volume almost doubles. And the way weather balloons actually work is that balloons eventually get so big that they pop. Just like if you inflate a balloon and you put too much air into it, the balloon gets too big and it pops. Same thing for the weather balloon. So Sam the dog up here, his balloon was a 6-liter balloon on the ground. As it got higher and higher and higher and higher into space, the balloon pressure decreased and its volume increased, and eventually the balloon got so big that it popped. And since there's not a balloon anymore there holding him on, he fell back down and he landed somewhere in a big field, and they were able to track him with the GPS. They were able to get the camera footage, and they were able to kind of show this video of this dog taking a little trip for a science class. And you can see how the pressures changed, how the temperature changed. They had a little thermometer in there, so they were able to measure the temperature at different heights and do all these calculations. So that's the combined gas law, looking at both pressure, volume, and temperature all at once. And as you change from one to the other, you can change any of these conditions. As long as you know 6 things here, as long as you know 5 of them, you can solve for the 6th piece. So those gas laws are useful if you have one gas at 2 different conditions. You want to see what happens to a balloon if you heat it up or cool it down, or what would happen to the pressure of a container as you changed its volume, or what would happen to the volume of something as you increase the temperature or decrease the temperature. And that's fine as long as you have one container at 2 different sets of conditions. But sometimes you might not want to do that. Maybe you just want to know what is the pressure inside a certain container at a certain temperature, and you don't want to heat it up to 2 different temperatures. You just want to know, what's the pressure inside my balloon at room temperature. And you can do that too, but we're going to use a different set of gas laws to do that, and that's called the ideal gas law. The ideal gas law is a different gas law, and that one uses one temperature, one volume, one pressure, but it also needs another bit of information as well. It needs 2 extra bits of information, the special value R and the special value N. But the nice thing about this gas law is that you don't need to change conditions. You keep the conditions the same throughout. And it's very similar units to what we had before. It still has a pressure measured in atmospheres. It still has a volume measured in liters. It still has a temperature measured in T, but it also needs the number of moles of gas. Moles of gas is going to be important for this particular equation, so it's something we have to be able to calculate. Need the special value of R, but R is kind of a known number, which is based on a certain factor, and then that's something we need to use. So we can figure out R based on a set of known conditions. So people have calculated R over various different conditions, and it's a known value. So it's 0.0821 liter atmospheres moles Kelvin. And that's based on studying lots of different gases over the years, and they found that basically 1 mole of any gas occupies a role of 22.4 liter volume at 1 atmosphere at 273 Kelvin or 0 degrees Celsius. And based on that, they were able to calculate this value of R. And that's the value we're going to use for all of our calculations with these ideal gas laws. So the ideal gas law, we're always going to have R 0.0821, but then we can use that R value to figure out the pressure or the volume or the number of moles of a gas. So this is just looking at an example here, right? So we have 7.6 moles of a gas. We have a volume of 12 liters, and we have a temperature of 293 K. So we can figure out what the pressure is by doing that. So you just have PV equals nRT. We're going to divide by V on both sides so that P is equal to nRT over V. And then it's just plugging in the values that we have. And then again, R is always equal to 0.0821 liter atmospheres per mole K. And you can see here, right, the moles here cancel with the moles in R. The liters down here cancel with the liters up here. The K here cancels with the K in R. And the only unit that we're left with is atmospheres. And that makes sense because we're working with atmospheres, because we're working with pressure. So we can use the ideal gas law to figure out the number of moles of a gas, the number of liters of a gas, the number of volume of a gas, or the pressure of a gas, as long as we have these other factors. So here we didn't have pressure, but we had number of moles, we had temperature, and we had volume. If we didn't have volume, but we had moles, temperature, and pressure, we could figure out volume. If we didn't know the temperature, we could figure that out as long as we know the number of moles, the volume, and the pressure. So this is the ideal gas law. This is only under one set of conditions. We're not changing temperature, we're not changing pressure, we're not changing volume, we're leaving those the same. And as long as we have moles, we can figure out the missing piece. So this is just another calculation right here. And this is looking at an ideal gas. So nitrogen is an ideal gas. Nitrogen actually happens to be used in tennis balls. And what we're trying to do is we're trying to figure out how many pressure units are inside a tennis ball. We've been given a temperature, we've been given a volume, and we've been given grams of gas. And we can use this temperature to figure out K, because we need to convert to K. We can use this volume here to figure out liters, and we can use this mass here to figure out moles. So we're going to have to convert all three of those into the right units, right? We can't just use grams of nitrogen because we don't have grams, we need moles. We can't just use cubic centimeters, we got to use liters. And we can't just use 24 degrees Celsius, we got to use kelvins. So let's do that one first. Kelvins is pretty easy to convert. So 24 degrees C, 24 degrees C plus 273, that means 297. So that's our temperature unit right here in kelvins, in the right unit to be using. So we've got our temperature now. So we've got one of the three things that we need to convert. The other ones are a little bit more complicated, but nothing too difficult. So we go over to our periodic table. We look up how much a nitrogen weighs. Turns out one nitrogen weighs 14. That means that two nitrogens weigh 28. Since two nitrogens weigh 28, we can put those in as well. So two nitrogens weighing 28 there. So we have our mass of nitrogen, grams of nitrogen, divided by the grams of nitrogen in a mole of nitrogen. So we've turned our grams of nitrogen into moles of nitrogen. Turns out that we have 0.0118 moles of nitrogen. So we've got our T, we've got our N. Now we just need our volume. And once we have V, T, and N, we can plug in R and we can get the pressure of the gas. So let's do that as well. We had 144 cubic centimeters. We got to convert cubic centimeters into milliliters. Turns out that 1 milliliter is equal to a cubic centimeter. So our centimeter 3 here cancels with our cm3 here. And then we have to turn milliliters into liters. There's 1,000 milliliters in 1 liter, so milliliters cancel. And we've turned cm3 into liters. So now we have our V, and our V is 0.144 liters. So we've got a temperature, a volume, number of moles. We can solve for pressure. So we put this into the ideal gas law. PV equals nRT. Let's get rid of P, divide by P right here. Do that. P equals nRT over V. Well, where's N? N is right here, 118. There's N. R is given, so R is always the same. So we plug in our value for R, 0.0821, and that would be on our equation sheet. We also need our volume. Our volume is right here. So we plug that in. And then the last thing is our temperature here. Plug in our temperature there. And if we do that, 0.0118 moles times 0.0821 liter atmosphere mole Kelvin times 297 Kelvin divided by 0.144 liters, you'd get 1.998. And let's just check our units, cancel out. So if we look at our units, moles cancel with moles, Kelvin cancels with Kelvin, liters cancels with liters. The only unit that's left is atmospheres, and atmospheres are the units that are in the final answer. So we know we set this up right. We solved everything. We turned our kelvins to Celsiuses to Kelvin, turned our centimeters to liters, turned our grams to moles, and that gave us the final set of results here for this experiment. And we got the final answer right here, and it makes sense given what the unit was supposed to be. So that's how you can use this ideal gas law to figure out something you don't know at a single temperature or a single pressure or a single volume. The other thing about ideal gases is that you can figure out how an ideal gas behaves by looking at to figure out the molecular weight of a gas. So if you don't know what kind of gas you're working with, you could do that as well, right? So we have our regular ideal gas law, PV equals nRT. We also know that N, if we rearrange this, right? So N equals RT. So let's divide by RT over here to give us this equation rearranged. N equals to PV over RT. We also know that N, the number of moles, is just equal to the mass of the molecule divided by its molecular mass. So we can use that as well. And we can kind of plug in to this. Mass over molecular mass is equal to PV over RT. And then we can rearrange to figure out what the molecular mass of a gas is. So molecular mass is just mass times R times T divided by P times V. And that would be if you had a gas and you didn't know what the gas was, but you knew how much it weighed. So if you knew that your tennis ball had 0.33 grams of some gas and you knew what its pressure was, you could actually figure out what gas is inside that object. So this is very useful for figuring out the molecular weight of a molecule or determining the identity of an unknown gas, as long as you know the mass of the gas, its temperature, and what pressure and volume it's at. So if you had a tank of gas and you don't know what it is, but you know how big the tank is, you know what the pressure is, you know what the temperature is, you could weigh the gas inside the tank and figure out what gas that is by its molecular weight or its molecular mass. And that's an example of what we're doing right here. We have this gas, 142 grams of a gas. We know it takes up 22.4 liters and a 2 atmosphere pressure at basically room temperature. And we don't know what the gas is, but we can figure it out by using this equation, right? The mass of the gas, 142, times R. R is always going to be the same value, 0.0821 liter atmospheres per mole Kelvin. And then we're going to multiply by the temperature, 273 Kelvin. Divide that by the pressure of 2 atmospheres, divide that by the volume of 22.4 liters. And if we do that, we get a molecular weight of 71 grams per mole. So whatever gas we're working with has a molecular weight of 71 grams per mole. And if this was an exam, you'd kind of look and see, all right, well, which one matches that? Turns out that Cl2 has a molecular mass of 71 grams per mole. 1 Cl weighs 35, 2 Cls weigh 71. So the gas that we're looking at in this case is probably Cl2 because that's the molecular mass for that particular gas. So these are ideal gases in an ideal gas law, and that's a little bit different than the real gases that we're working with, but because no gas actually behaves completely like an ideal gas. Real gases are going to be slightly different. There's a little bit more attractions between those molecules. So really big molecules or nonpolar molecules, those may behave a little bit differently. If the temperatures are really, really high or really, really low, they may behave differently. If the pressure is really, really high or really, really low, those may behave differently. But for the most part, gases do behave the same way as an ideal gas, but the numbers may not be 100% correct. So if you're doing these calculations and your numbers are off a little bit from the ideal gas compared to the actual behavior, so if you calculated the mass to be 71.05 and you think the mass should have been 71.0, that's okay because not every gas behaves exactly like an ideal gas. There's going to be some minor fluctuations, but mostly they behave about the same way. So that's a good spot to stop for today, talking about the two different types of gases laws for ideal gases versus gases at different pressures or different temperatures. And if you have any questions or any comments, there's a discussion board on Blackboard to post questions to for clarification or for going over things, and we'll use that as a way of kind of doing in-class questions. And have a good night and have a good day. Bye.